January 4th, 1945. Lieutenant Junior Grade Charles August pushed the throttle forward on his F6F Hellcat, Bureau number 71441, as the carrier USS Langley pitched beneath him. The 2,000 horsepower Pratt & Whitney R2800 double wasp engine roared to life, and within seconds he was airborne, climbing into the grey winter sky over the Pacific. His target, Kobe Airfield on Formosa. His mission, escort TBM Avengers in a strike against Japanese installations, then strafe targets of opportunity. August had done this dozens of times before. The Hellcat beneath him was a proven warrior, fast, heavily armed, nearly indestructible. Every American pilot knew the score by late 1944. The Hellcat dominated the Pacific skies with a 19-to-1 kill ratio. Japanese fighters were outmatched, outgunned, and increasingly flown by inexperienced pilots. This should have been another routine mission. Then, at approximately 10:00 hours, after the strike on the airfield was complete, August's engine began losing power. Oil pressure dropped. The temperature rose. Something in that massive 18-cylinder radial engine, the heart that gave the Hellcat its overwhelming advantage, was failing. August radioed his flight leader, banked away from his formation, and began scanning the ground below for a place to put down. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. He spotted what appeared to be flat ground near the airfield, lowered his landing gear, and brought the crippled Hellcat in for an emergency landing. The belly landing was textbook perfect. The Hellcat slid across the field, came to rest, and August climbed from the cockpit unhurt. Within minutes, Japanese soldiers surrounded him. He was captured, bound, and led away. The Hellcat remained where it had landed. By August, the war was over. He would spend the next 9 months in a prisoner of war camp near Tokyo, enduring brutal conditions but ultimately surviving to be liberated when Japan surrendered. But for the Japanese engineers who examined the aircraft he left behind, a different kind of ordeal was just beginning. They were about to discover the true extent of the technological chasm that separated their aircraft from America's. The story of what happened next, of what those engineers found when they took that Hellcat apart, reveals one of the most profound disparities in World War II. Not the disparity in courage or tactical skill, but the disparity in industrial capacity and engineering philosophy that made American victory in the Pacific not just likely, but inevitable. This is not a story about a single battle or a single pilot. It is the story of how Japanese aviation engineers, some of the most talented in the world, confronted evidence they could not deny. Evidence that the war they were fighting could not be won. Evidence wrapped in aluminum, steel, and 2,000 horsepower of American engineering that they literally could not comprehend. The belief system that would be shattered began years earlier, in the late 1930s, when Japanese aviation was genuinely world-class. The Mitsubishi A6M0 fighter, which first flew in April 1939, represented the cutting edge of carrier-based fighter design. It combined exceptional range, excellent maneuverability, respectable firepower, and adequate speed in a package light enough for carrier operations. The Zero was powered by a Nakajima Sakae 12 radial engine producing 940 horsepower. This 14-cylinder, twin-row air-cooled engine was a capable power plant, derived from earlier Nakajima designs and incorporating knowledge gained from studying American and European engines. The Japanese aviation industry had learned much from foreign technology. Before the war, Japan had contracts with Pratt & Whitney and other American manufacturers. Some early Japanese aircraft actually flew with American engines. The Sakai engine represented what Japanese engineers could accomplish when they applied this foreign knowledge to their own designs. It was reliable, relatively fuel-efficient, and produced sufficient power for the Zero's intended mission. At 940 horsepower, it was comparable to engines powering many contemporary fighters around the world in 1939 and 1940. What the Zero lacked in raw power, its designers compensated for through weight savings. Chief designer Jiro Horikoshi and his team at Mitsubishi had created an airframe that weighed just 5,300 pounds, fully loaded in its early variants. This was achieved through careful engineering, use of lightweight materials, and, most controversially, the elimination of features Western designers considered essential. The Zero had no armor protection for the pilot. The fuel tanks were not self-sealing. The airframe was built to minimum structural tolerances with no safety margins for combat damage. These were not oversights. They were deliberate design choices, driven by the Imperial Japanese Navy's requirements and by the limitations of available engine power. In dogfights over China beginning in 1940, the Zero proved devastatingly effective. It could outclimb, outturn, and outrange any aircraft the Chinese could field. When war broke out across the Pacific in December 1941, the Zero achieved similar dominance over American, British, and Dutch aircraft. In the 6 months following Pearl Harbor, Zero pilots racked up victory after victory. Allied pilots developed a healthy respect for the Japanese fighter that bordered on fear. This success created confidence, even pride, among Japanese aviation engineers and military planners. The Zero represented Japanese ingenuity, triumphing over material limitations, where American designers relied on brute force, more power and heavier construction. Japanese designers achieved superiority through elegance and efficiency. The philosophy worked. The results spoke for themselves. But this philosophy rested on assumptions that would not survive contact with American industrial mobilization. American aircraft design in the early war years followed a different path, where Japanese designers prioritized maneuverability and range over protection. American designers increasingly emphasized pilot survivability and structural ruggedness. Where Japanese engineers worked within the constraints of limited engine power, American engineers had access to steadily increasing horsepower from an aviation industry that was rapidly expanding. The Grumman F6F Wildcat, America's frontline carrier fighter in 1941 and 1942, illustrated this philosophy. It was heavier than the Zero, weighing over 7,000 pounds fully loaded. It had armor plate, protecting the pilot, self-sealing fuel tanks, and robust construction. It was powered by a Pratt & Whitney R1830 twin Wasp engine, producing 1,200 horsepower. In combat, the Wildcat could not turn with the Zero. It could not outclimb the Zero. In a traditional dogfight, the Zero held every advantage. Yet Wildcat pilots developed tactics that exploited their aircraft's strengths: superior diving speed, better high-speed performance, heavier construction that could absorb battle damage. The Thach Weave, developed by Lieutenant Commander John Thach, used pairs of Wildcats flying mutual support patterns to negate the Zero's turning advantage. These tactics kept American carrier aviation in the fight through the dark days of 1942. But they were defensive measures, ways to survive rather than dominate. American planners knew a better fighter was needed. The question was how to achieve it. The answer arrived through multiple channels. Combat. Experience from pilots who had fought Zeros provided crucial information about the Japanese fighters' capabilities and limitations. Intelligence reports filled in technical details, and in June 1942, luck provided an almost intact Zero for examination when Petty Officer First Class Tadayoshi Koga crash-landed on Akutan Island in the Aleutians, dying in the impact but leaving his aircraft largely undamaged. American engineers recovered the Akutan Zero in July 1942, transported it to San Diego, repaired it, and began extensive flight testing in September. Test pilots discovered the Zero's specific weaknesses. Its ailerons froze up at speeds above 200 knots, making high-speed rolls difficult. The float-type carburetor caused the engine to quit under negative gravity, stalling during certain maneuvers. The lightweight construction made the aircraft fragile. These were exploitable vulnerabilities, but more important than the tactical intelligence was the strategic realization the capture provided. The Zero was not invincible. It was not a superweapon created by enemy genius beyond American comprehension. It was an aircraft with specific design trade-offs, optimized for certain conditions, vulnerable in others. It could be beaten by an aircraft designed with its weaknesses in mind. Grumman Aircraft Engineering Corporation on Long Island, New York, had been working on a Wildcat replacement since 1938. The contract for the prototype XF6F1 was signed on June 30th, 1941, 6 months before Pearl Harbor. The initial design called for a Wright R2600 Cyclone engine producing 1,700 horsepower, a significant increase over the Wildcat's 1,200. But as combat reports from the Pacific accumulated through early 1942, Grumman engineers and Bureau of Aeronautics officials recognized that incremental improvements would not suffice. The new fighter needed overwhelming advantages to ensure American pilots could defeat Zero pilots regardless of tactical circumstances or pilot experience levels. On April 26, 1942, before the Akutan Zero was even discovered, the Bureau of Aeronautics made a critical decision. They directed Grumman to install a more powerful engine in the second XF6F prototype. The Wright R2600 was abandoned in favor of the Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial engine producing 2,000 horsepower. This engine represented everything the Zero's Nakajima Sakai was not. Where the Sakai produced 940 horsepower, the R2800 produced 2,000. Where the Sakai weighed approximately 1,200 pounds, the R2800 weighed over 2,000. Where the Sakai displaced just 27.9 litres, the R2800 displaced 46 litres. The difference was not merely quantitative, it was philosophical. The R2800 represented American engineering at scale, an engine designed without the resource constraints that limited Japanese development. It incorporated advanced metallurgy, precision manufacturing, and sophisticated engineering solutions that pushed the boundaries of what was possible in aircraft engine design. The engine choice shaped everything that followed. To handle the R2800's power and weight, the F6F airframe had to be substantially larger and stronger than the Wildcat. The structure had to absorb harder carrier landings. The wings had to generate more lift. The landing gear had to support greater weight. Every system had to be scaled up, but the power made these penalties worthwhile. The XF6F3, fitted with the R2800, first flew on July 30th, 1942. Test pilots immediately recognized they had something special. The aircraft was fast, approaching 380 miles per hour at optimal altitude. It climbed rapidly, reaching 20,000 feet faster than a Zero could reach 15,000. It had excellent visibility from the raised cockpit position. Most importantly, it felt solid, substantial, a fighter that could take punishment and keep flying. Grumman engineers incorporated lessons from the Akutan Zero examination as they finalized the F6F design through late 1942. The ailerons were hydraulically boosted and metal-covered, maintaining full control authority at all speeds. The fuel system used a pressure carburetor that would not quit under negative acceleration. The structure was designed to handle 9G positive and 6G negative acceleration without failure. The cockpit was protected by 200 pounds of armor plate behind the seat and bulletproof plexiglass in the windscreen. Self-sealing fuel tanks prevented catastrophic fires from bullet strikes. Redundant systems ensured that damage to one area would not cripple the entire aircraft. The F6F was designed to bring its pilot home even after absorbing damage that would destroy a Zero. Armament reflected American firepower philosophy. 6 50-caliber machine guns, 3 in each wing, provided devastating offensive capability. Each gun could fire 1,000 rounds per minute. Against the Zero's lightweight construction and unarmored fuel tanks, short bursts were often sufficient to destroy the target. Later, F6, F5 variants would offer the option of 2 20mm cannons and 4 50-caliber guns for even greater hitting power. Production began at Grumman's Bethpage, Long Island facility in October 1942. The first production F6 F3 made its maiden flight on October 4th. 3 months later, in January 1943, the first operational Hellcats reached fleet squadrons. Fighting Squadron 9 embarked on the carrier Essex in March with the new fighters. The speed of development was remarkable. From first flight of the Kami, XF6F 1-inch June 1942, to operational deployment in January 1943, just 19 months elapsed. This was possible only because of America's industrial capacity and the urgency driving the program. Every week's delay meant more American pilots facing zeros in inferior aircraft. Grumman ramped up production with astonishing rapidity. In December 1942, as the first production aircraft were being completed, Grumman produced 97 Hellcats. By mid-1943, production exceeded 500 aircraft per month. The Bethpage factory operated 3 shifts, 24 hours per day, 7 days a week. Workers included men from the pre-war aviation industry and thousands of women, many of whom had never worked in heavy manufacturing before the war. The production line was organized for maximum efficiency. Subcontractors produced components, frames, skin panels, control surfaces, landing gear, instrument packages, which were shipped to Bethpage for final assembly. Pratt & Whitney engines arrived from separate factories and were installed as complete units. The entire process, from raw materials to finished aircraft, took approximately 30 days. Quality control was rigorous. Every aircraft was test-flown before delivery to the Navy. Defects were corrected immediately. The goal was not just quantity but consistent quality, ensuring every Hellcat that reached a carrier squadron was combat-ready. By early 1944, Hellcats equipped 15 carrier fighter squadrons and were rapidly becoming the dominant American naval fighter in the Pacific. The aircraft's combat debut had occurred in September 1943 during attacks on Marcus Island. No Japanese fighters managed to get airborne, and the Hellcats destroyed several aircraft on the ground, losing 2 aircraft to anti-aircraft fire, but none in air-to-air combat. The real test came on November 23, 1943, when F6F Hellcats from carrier Essex engaged Japanese Zero fighters over Tarawa in the Gilbert Islands. 30 Zeros rose to intercept the American strike. The ensuing dogfight raged across the skies over the invasion beaches. When it ended, American pilots claimed 30 Japanese fighters were destroyed for the loss of a single F6F. The Battle of Tarawa demonstrated everything the F6F was designed to accomplish. American pilots, many relatively inexperienced, had met veteran Japanese aviators flying Zeros and defeated them decisively. The combination of superior aircraft performance, sound tactics based on knowledge of the Zero's weaknesses, and intensive training had created a formula for overwhelming victory. For Japanese naval aviation, Tarawa was an omen of things to come. The age of Zero supremacy was ending. American industry had produced a fighter that could beat the Zero on technical merit, not just through tactical cleverness, and production was accelerating. Grumman was building Hellcats faster than Japan was building Zeros. But the full extent of the technological disparity would not become clear until Japanese engineers had the opportunity to examine a Hellcat themselves. Not just observe it in combat, where factors like pilot skill and tactical circumstances complicated analysis, but take one apart, measure every component, test every system, and confront the reality of what American industry had created. That opportunity came on January 4, 1945, when Lieutenant Junior Grade Charles August made his emergency landing on Formosa. The Japanese quickly secured the aircraft, noting with satisfaction that it was largely intact. Minor damage from the belly landing, but the airframe was sound, the engine apparently salvageable, all systems present. This was an intelligence windfall. The Hellcat, Bureau number 7, 1441, tail code 29, was carefully moved to Kobe Airfield for initial examination. Photographs taken at this time show the aircraft sitting on its landing gear, wings folded, surrounded by curious Japanese personnel. The American insignia had been hastily overpainted with Japanese Hinomaru markings, and the tail code Yo801, designation of the Yokosuka Kokutai, had been applied, complete with paint drips suggesting the hurried nature of the work. The aircraft was then transported to the Yokosuka Naval Air Technical Arsenal near Tokyo, the primary facility for evaluating captured enemy equipment. Here, the real examination would begin. Japanese aviation engineers and test pilots would have the opportunity to fly the Hellcat, test its performance, disassemble its systems, and learn what they could from America's premier carrier fighter. What they discovered would force them to confront uncomfortable truths about the war they were fighting. The Yokosuka Naval Air Technical Arsenal sprawled across several hundred acres on the western shore of Tokyo Bay. This was where the Imperial Japanese Navy brought its most advanced projects and its most pressing problems. Engineers here had designed the D4Y Suisei dive bomber, developed improvements to the Zero, and tested experimental aircraft intended to turn the tide of war. In early 1945, the facility was working under increasingly desperate conditions. American submarines had severed most supply lines to Southeast Asia, cutting off access to critical raw materials. 29 bombers were beginning to strike industrial targets across Japan. The Navy's carrier air groups had been decimated in the Battle of the Philippine Sea the previous June. Resources were scarce, time was running out, and everyone at Yokosuka knew it. Into this environment arrived the captured Hellcat, a tangible example of what Japan was facing. Senior engineer Teruo Miyoshi, a former Imperial Japanese Army radioman who had extensive experience evaluating captured American aircraft, was among those assigned to examine the Hellcat. Years after the war, he would write about the evaluation process and the detailed briefings given to Japanese pilots about American aircraft capabilities. His writings provide rare insight into how Japanese engineers perceived the Hellcat and what conclusions they drew from examining it. The first assessment focused on the most obvious feature, the massive engine occupying the Hellcat's nose. Japanese engineers immediately recognized it as a Pratt & Whitney R2800 Double Wasp, the same engine that powered the Republic P-47 Thunderbolt and the Vought F-4U Corsair. They had heard reports of this engine from combat pilots, but seeing it disassembled on a test stand was different. The R2800 displaced 2,804 cubic inches, 46 litres. It had 18 cylinders arranged in 2 rows of 9. It was an air-cooled radial, like the Nakajima Sakai that powered the Zero, but there the similarities ended. Where the Sakai produced 940 horsepower, the Double Wasp produced 2,000. The difference was staggering, more than double the power from an engine that was larger, yes, but not proportionally larger. Japanese engineers carefully measured and documented the engine components. The cylinders were massive, each one machined to precise tolerances from high-grade aluminum alloy. The crankshaft was forged steel, balanced to exacting standards to handle the tremendous forces generated by 18 pistons firing in sequence. The supercharger was a sophisticated 2-stage unit that maintained power output at high altitudes. The entire assembly weighed approximately 2,100 pounds. The sophistication of the manufacturing was evident in every component. Tolerances that Japanese industry struggled to achieve in small quantities were maintained throughout this engine, which was being produced by the thousands. The metallurgy was advanced, using alloys and heat treatments that Japanese engineers recognized as superior to their own. One engineer, examining the cylinder heads, noted that the fin spacing and design provided exceptional cooling efficiency. The entire engine was designed for extended operation at high power settings without overheating, something Japanese engines struggled with. The Nakajima Sakai could produce its rated power for limited periods, but sustained high-power operation risked overheating and mechanical failure. The Double Wasp could apparently run at maximum power indefinitely. The fuel system used a sophisticated pressure carburetor with automatic mixture control. This was far more advanced than the float-type carburetors used in Japanese engines. The pressure carburetor ensured proper fuel delivery regardless of aircraft attitude, solving the problem that plagued the Zero, where negative acceleration caused the engine to quit. Japanese engineers recognized this as a significant advantage in combat, where violent maneuvers were commonplace. The ignition system featured dual magnetos, providing redundancy. If one magneto failed, the engine would continue running on the other. Japanese aircraft typically had single ignition systems. Engine failure meant landing immediately if possible, or ditching if not. The Hellcat's redundancy meant the pilot might not even notice a magneto failure, continuing the mission on the remaining system. As engineers documented these features, a realization began to form. This was not just a more powerful engine, it was a fundamentally different approach to engineering. Where Japanese designers built engines to minimum specifications, accepting limitations as unavoidable given resource constraints, American designers built engines with performance margins, redundancy, and durability that suggested resources were essentially unlimited. The economic implications were staggering. Each R2800 required thousands of man-hours to manufacture, access to high-grade materials, sophisticated machine tools, and rigorous quality control. Yet Pratt & Whitney was producing these engines in quantities sufficient to power 3 separate fighter programs, the Hellcat, the Corsair, and the Thunderbolt, plus various other aircraft. The scale of production was almost incomprehensible. Moving beyond the engine, engineers examined the Hellcat's airframe. Here, too, they found evidence of design philosophy radically different from Japanese practice. The fuselage was built from aluminum alloy formers and stringers, covered with aluminum skin riveted in place. This was similar to Japanese construction techniques, but the execution was different. The structural members were heavier than comparable Japanese components. Where Japanese designers used the minimum material necessary, American designers appeared to have included safety factors. The result was an airframe that weighed significantly more, over 12,000 pounds fully loaded for the Hellcat versus 6,100 pounds for the later Zero models, but could withstand far greater stress. Japanese engineers conducted structural tests on sections of the airframe. They found that the Hellcat could handle 9 positive and 6 negative G-forces before structural failure. By comparison, the Zero's airframe was rated for 7 positive G and 4 negative G. The difference meant Hellcat pilots could execute more violent maneuvers without fear of breaking their aircraft, while Zero pilots had to be mindful of structural limits. The phrase "extremely strong construction" appeared repeatedly in Japanese evaluation reports. This strength came at a weight penalty that would have been unacceptable in a Japanese fighter, but the powerful engine made it feasible. The Hellcat could afford to be heavy because it had power to spare. Armor protection amazed Japanese engineers. Behind the pilot's seat was a thick plate of face-hardened steel armor weighing over 100 pounds. Additional armor protected the oil, cooler, and other critical components. The windscreen was made of bullet-resistant glass laminate that could stop small arms fire. The fuel tanks were self-sealing, with rubber bladders that automatically closed bullet holes to prevent fuel loss and fires. Japanese aircraft had minimal armor protection. The Zero's pilots sat behind a single thin armor plate and had no frontal protection. Fuel tanks were not self-sealing until very late in the war, and even then, the sealing was less effective than American designs. This was not because Japanese engineers did not understand the value of protection. It was because protection costs weight, and weight requires power, and power was something Japanese engines could not provide without sacrificing other capabilities. The Hellcat's armament impressed through its sheer volume of firepower. 6 Browning 50 caliber machine guns, 3 in each wing, with 400 rounds per gun. The total ammunition load was 2,400 rounds. Each gun could fire approximately 800 rounds per minute. When all 6 guns fired simultaneously, the Hellcat was putting out 4,800 rounds per minute, 80 rounds per second. Japanese engineers calculated the weight of fire. Each 50 caliber round weighed approximately 1.6 ounces. 80 rounds per second meant over 128 ounces, 8 pounds of projectiles per second streaming toward the target. For comparison, the Zero's 2 7.7mm machine guns and 2 20mm cannons delivered approximately 4 pounds of projectiles per second, less than half the Hellcat's output. The 50-caliber Browning M2 machine gun was itself a sophisticated weapon. Belt-fed, recoil-operated, capable of sustained fire without overheating, it represented decades of American weapons development. The ammunition included armor-piercing, incendiary, and tracer rounds in mixed belts. Against the Zero's unarmored construction, even short bursts were often fatal. But perhaps more significant than any individual component was the overall integration. The Hellcat was designed as a complete weapons system, where every element reinforced the others. The powerful engine enabled the heavy armor and armament. The strong airframe could withstand violent maneuvers and hard carrier landings. The sophisticated systems provided reliability and redundancy. The result was an aircraft that was greater than the sum of its parts. Japanese engineers preparing briefings for pilots summarized their findings. According to Miyoshi's later account, the briefings emphasized several key points. The Hellcat was sturdy and simple, another masterpiece of the so-called Grumman Ironworks. It was essentially a larger, faster development of the F4F Wildcat. The huge 18-cylinder radial engine with 2,000 horsepower exceeded the Zero's power plant by more than double. The advantages were listed systematically. Sturdy. Grumman construction meant the aircraft could absorb battle damage. Easy to maneuver, though not as agile as the Zero. Speed and acceleration were excellent, superior to Japanese fighters at most altitudes. The aircraft was equipped with very heavy armament, 6 50-caliber machine guns that could destroy a Zero with brief firing. Bulletproof facilities were sturdy, meaning pilot protection was excellent by Japanese standards. The disadvantages were acknowledged honestly. The Hellcat was not the fastest American fighter, being slower than the P-51 Mustang. It was not as agile as the Zero fighter, particularly in low-speed turning combat, but the briefing also included tactical hints that revealed Japanese awareness of the mismatch. Because the Hellcat was agile and equipped with a powerful engine, combat at 18,000 to 21,000 feet was described as risky for Japanese pilots. One suggested tactic was to bring the opponent into low-altitude combat, where the Zero's maneuverability advantage was greatest. When attacked, Japanese pilots were advised to wrap against the enemy and attack from the front, making use of their firearms as much as possible. Showing the tail to a Hellcat was described as risky. The briefing noted that Hellcat pilots relied on teamwork tactics as insurance. Once the team was broken into 1-versus-1 fights, it was unexpectedly easy to fight them, but Japanese pilots needed to study how to break the formation first. Reading between the lines, these tactical suggestions revealed desperation. Japanese engineers and tacticians were telling their pilots to avoid combat at medium and high altitudes where the Hellcat's advantages dominated. They were advising pilots to try to break up American formations to negate tactical coordination. They were emphasizing frontal attacks despite the Hellcat's heavy frontal armor and powerful forward-firing armament. These were the tactics of the weaker force trying to survive, not the confident doctrines of an air force expecting victory. Test pilots at Yokosuka flew the captured Hellcat to verify the engineering assessments. The aircraft had been repaired after its belly landing, new propeller blades installed, minor airframe damage corrected, and systems checked. On a clear morning, probably in late January or early February 1945, a Japanese test pilot climbed into the cockpit for the first flight. The cockpit was spacious compared to the cramped confines of a Zero. The seat was comfortable, with proper cushioning. The instrument panel was logically laid out with large, clear gauges. Visibility was exceptional, with the pilot seated high in the fuselage, providing clear views in all directions. The American designers had taken pilot comfort and effectiveness seriously in ways Japanese designers, constrained by weight requirements, could not. Starting the engine required careful attention to the unfamiliar controls, but the double wasp caught on. The first try and settled into a smooth idle. The sound was different from Japanese engines, deeper, more powerful, a rumble rather than the higher-pitched note of the Nakajima Sakai. Taxiing revealed excellent ground handling. The tailwheel was steerable, and the brakes were effective. The takeoff run was short despite the aircraft's weight. The pilot advanced the throttle and felt 2,000 horsepower surging through the airframe. The Hellcat accelerated rapidly and lifted off after a ground roll that would have been respectable for a much lighter aircraft. The initial rate of climb was impressive, far exceeding what a Zero could achieve. At altitude, the test pilot put the Hellcat through a series of maneuvers. Rolls were slower than a Zero's, but still adequate. The ailerons remained effective at high speeds, something the Zero could not match. Loops and other vertical maneuvers were easy, the powerful engine pulling the heavy fighter through maneuvers that would have caused a Zero to lose energy and altitude. The Hellcat felt solid, stable, and predictable. There were no bad habits, no sudden surprises. It was an aircraft designed to be flown by relatively inexperienced pilots, fresh from training, and it showed. The Zero was a thoroughbred requiring skill and finesse. The Hellcat was a warhorse that anyone could ride. Speed trials confirmed what combat reports had indicated. The Hellcat was faster than the Zero at all altitudes. At sea level, the Hellcat had a slight edge. At 20,000 feet, where both aircraft were operating efficiently, the Hellcat was noticeably faster. At 30,000 feet, approaching the operational ceiling, the Hellcat still held a speed advantage. Climb rate comparisons were even more telling. The Hellcat could reach 20,000 feet in approximately 7 minutes. The Zero needed approximately 9 minutes to reach the same altitude. This meant that in any engagement where the Hellcat started from a lower position, it could climb to meet the Zero and still have energy for combat. Zero pilots could no longer rely on superior climb performance to escape. Diving speed was dramatically different. The Hellcat could dive at speeds approaching 450 miles per hour without structural problems. The Zero's lighter construction limited safe diving speed to approximately 350 miles per hour. Any attempt to follow a diving Hellcat risked structural failure as the airframe exceeded design limits. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The test pilot noted in his report that the Hellcat's advantages in speed, climb, and dive meant it could dictate engagement terms. If the tactical situation favored combat, the Hellcat could engage. If not, it could escape with confidence that no Zero could catch it. Japanese fighters had lost the ability to force combat or avoid it as circumstances dictated. The initiative had passed entirely to the Americans. After test flights were complete, engineers at Yokosuka compiled comprehensive reports on the Hellcat's capabilities. These reports were distributed to training units and operational squadrons throughout what remained of Japanese naval aviation. Pilots received detailed briefings on how to fight the Hellcat, or more accurately, how to survive encounters with it. But beyond the tactical implications, the captured Hellcat forced Japanese engineers to confront broader questions about the war. This aircraft represented American industrial and technological capability at a level Japan simply could not match. Every component, from the massive engine to the sophisticated systems to the heavy armor to the powerful armament, required manufacturing capabilities and material resources that Japan lacked. The engineering philosophy behind the Hellcat was fundamentally different from Japanese practice. Where Japanese, designers had to make agonizing trade-offs, sacrificing protection for performance or range for armament, American designers appeared to have simply said yes to everything, yes to heavy armor, yes to a powerful engine, yes to massive armament, yes to sophisticated systems, yes to rugged construction. This was possible only because America had industrial resources on a scale Japan could not comprehend, let alone match. The distance between what Japan needed and what Japan could produce was growing wider every month, and the captured Hellcat was tangible proof of that gap. Japanese aircraft production in 1944 totaled approximately 28,000 aircraft of all types. This included fighters, bombers, trainers, reconnaissance aircraft, transports, everything the Japanese military needed. Of these, perhaps 5,000 were fighters, including both Army and Navy aircraft. Zero production in 1944 was approximately 2,300 aircraft, American aircraft production in 1944 totaled 96,318 aircraft of all types. Fighter production alone exceeded 38,000 aircraft. Hellcat production in 1944 was approximately 6,147 aircraft, more than triple Japanese Zero production. The numbers were not merely different in scale, they represented entirely different economic realities. Japan was a nation of approximately 73 million people, with limited natural resources, dependent on conquering territory to obtain oil, rubber, metals, and other strategic materials. By 1945, American submarines had severed most of those supply lines. The Japanese industry was starving for raw materials. America was a nation of 139 million people, with vast natural resources, continental territory that could not be threatened, and an industrial base that had been mobilized for total war. The arsenal of democracy that President Roosevelt had promised in December 1940 was not rhetorical flourish, it was reality. Grumman Aircraft Engineering Corporation operated one major production facility for the Hellcat at Bethpage, Long Island. This single factory produced 12,275 Hellcats between October 1942 and November 1945. Peak production reached 644 aircraft in March 1944, one Hellcat every hour. The facility employed approximately 25,000 workers at peak production. Many were women who had entered the workforce for the first time due to wartime labor needs. They welded airframes, assembled components, installed systems, riveted skin panels, and performed every task in the manufacturing process. The quality of their work was consistently high, defect rates were low, aircraft were delivered on schedule. This was repeated across hundreds of factories throughout America. Republic Aviation in Farmingdale, New York, was building P-47 Thunderbolts, also powered by the R-2800 engine. North American Aviation in California was building P-51 Mustangs. Douglas Aircraft was building dive bombers and attack aircraft. Boeing was building B-17 and B-29 heavy bombers. Consolidated Aircraft was building B-24 heavy bombers and PBY patrol aircraft. The scale was staggering. In December 1942 alone, American factories produced 9,625 aircraft. In December 1943, production reached 11,327. In December 1944, at the peak of wartime production, American factories delivered 9,598 aircraft in a single month. Japanese engineers examining the captured Hellcat understood what these numbers meant. They were not fighting a nation, they were fighting an industrial colossus that could replace losses faster than Japan could inflict them, that could develop and field new weapons while simultaneously mass-producing current designs, that could supply two separate theatre commands in Europe and the Pacific, while providing massive aid to allies. The comparison extended to every aspect of military capability. American carriers operated with full air groups, including fighters, dive bombers, and torpedo bombers. Japanese carriers, those few that remained operational, struggled to field partial air groups due to aircraft and pilot shortages. American surface combatants had radar-directed fire control, advanced damage control systems, and sophisticated electronics. Japanese ships had increasingly obsolete equipment and untrained crews. American submarines dominated the Western Pacific, sinking Japanese merchant shipping faster than it could be replaced. By early 1945, Japan's merchant marine had been reduced to a fraction of its pre-war size. Oil tankers could barely reach Japan from the Dutch East Indies. Food shipments from Southeast Asia had nearly stopped. The home islands were slowly being strangled. Japanese aviation fuel production had collapsed. High-octane aviation gasoline required sophisticated refining and specific additives. As American bombing intensified and supply lines were cut, fuel quality decreased. Pilots began experiencing engine failures due to poor fuel. Training flights were curtailed to conserve fuel. New pilots entered combat with perhaps one-third the flight hours American pilots received, making them easy prey for experienced American aviators flying superior aircraft. The captured Hellcat represented all of this in microcosm. It was not just an aircraft, it was evidence of overwhelming American material superiority. Every component, every system, every design choice reflected resources and capabilities Japan could not match. Some Japanese engineers had understood this from the beginning. They had visited American factories before the war, seen the production lines, and comprehended the scale. They had advised against war with America, warning that Japan could not win an extended conflict against such industrial might. They had been ignored. Political and military leaders had convinced themselves that Japanese fighting spirit and tactical skill would overcome material disadvantages. Those early victories would demoralize Americans and lead to negotiated peace. By January 1945, those illusions were shattered. Early victories had bought time, nothing more. Americans had not been demoralized. They had been angered, and now the full weight of American industrial power was crushing Japan methodically and inevitably. The engineers at Yokosuka could see the end approaching, not because they lacked technical skill or understanding, but because they understood too well. They knew what resources would be required to develop aircraft that could match the Hellcat. They knew Japan did not have those resources and could not obtain them. They knew that every day, the technological gap widened as American industry continued advancing, while Japanese industry struggled merely to maintain production of existing designs. Advanced Japanese fighters existed on paper and in limited prototypes. The Kawanishi N1 KJ Shiden had entered limited production, a land-based fighter with performance approaching the Hellcat. The Mitsubishi A7M Repu was under development, intended as the Zero's successor with a 2,000 horsepower engine. These aircraft might have been competitive, but they would never be produced in sufficient numbers to affect the war's outcome. Manufacturing the Repu's Mitsubishi Mk9, a 18-cylinder engine, required materials and machine tools Japan no longer had reliable access to. The few prototypes built showed promise, but transitioning to mass production was impossible. Even if production could begin, how many could be built? Hundreds? A few thousand? America would respond by building tens of thousands of even more advanced fighters. The mathematics of industrial warfare were brutal and unyielding. Japan had gambled that spirit could defeat material, that early victories would reshape the strategic balance, that America would negotiate rather than fight. All three assumptions had proven false, and the price of that miscalculation was becoming clear. The captured Hellcat sat at Yokosuka for several months. Engineers continued examining it, documenting every detail, learning what they could. Test pilots flew it occasionally, comparing its performance against Japanese fighters. The results were always the same. The Hellcat was faster, climbed better, dived faster, and was far more durable. When American forces occupied Japan after the surrender in August 1945, they found the Hellcat at Yokosuka Naval Air Station. It was damaged, possibly from air raids or maybe deliberately to prevent it from being flown. The American insignia was still visible beneath the faded Japanese markings. The bureau number, 71441, remained on the tail. Photographs were taken documenting the captured aircraft in Japanese service. Then it was likely scrapped, one more piece of war debris among millions. Its intelligence value had long since been exhausted. The information it provided had been distributed throughout Japanese aviation and had not changed the war's trajectory 1 degree. But the story it tells extends beyond one aircraft. The Hellcat that Lieutenant Junior Grade Charles August left on Formosa represented the technological and industrial chasm between America and Japan in the final year of World War II. Japanese engineers who examined it understood what they were seeing, understood its implications, understood that the war was lost not through any failure of courage or skill, but through overwhelming material disadvantage. The story of the captured Hellcat exists within a larger narrative of Japanese aviation's decline, through 1944 and 1945. Understanding what that single aircraft meant to Japanese engineers requires understanding the broader context in which they examined it, a context of cascading defeats, collapsing infrastructure, and diminishing hope. The Battle of the Philippine Sea in June 1944 had been catastrophic for Japanese naval aviation. American pilots called it the Great Marianas Turkey Shoot, a name that captured the one-sided nature of the slaughter. Japanese carriers launched 370 aircraft in multiple strikes against Task Force 58. Only 130 returned. American losses totaled 23 to 30 aircraft, many of which ditched due to fuel exhaustion after pursuing fleeing Japanese aircraft, with most pilots rescued. The destruction was not merely numerical. The carrier air groups Japan had painstakingly rebuilt after the disasters at Midway and Guadalcanal were annihilated. Experienced pilots who had survived earlier battles and trained the current generation were dead. The pilots who replaced them had minimal training due to fuel shortages and the accelerating pace of the war. Average flight time for Japanese pilots entering combat in late 1944 was perhaps 300 hours compared to 600 or more for American pilots. The disparity showed immediately in combat. American pilots with hundreds of hours in type, flying F6F Hellcats with overwhelming technical advantages, faced Japanese pilots with minimal experience flying Zeros or other fighters that were outmatched in nearly every category. The results were predictable. Combat became execution. The 19-to-1 kill ratio the Hellcat achieved over its service life was not merely due to technical superiority. It reflected the combination of better aircraft, better trained pilots, better tactics, and numerical superiority that characterized American naval aviation by mid-1944. Japanese commanders understood what was happening. Intelligence reports from surviving pilots described the Hellcat's capabilities. Combat after action reviews documented the mismatch. But understanding the problem and solving it were different things. Japan could not produce Hellcats. It could barely produce Zeros in sufficient numbers. Mitsubishi and Nakajima, the primary Zero manufacturers, struggled with material shortages through 1944. Aluminum alloys required bauxite imports from the Dutch East Indies. Copper for electrical systems came from occupied territories. High-grade steel for engine components needed chromium and other alloying elements obtained through trade or conquest. American submarines were systematically severing these supply lines. By January 1945, when Charles August's Hellcat arrived at Yokosuka, Japanese merchant shipping losses had reached catastrophic levels. Of the approximately 6 million tons merchant shipping Japan possessed at the war's start, fewer than 2 million tons remained operational. Tankers were priority targets for American submarines. Oil imports from the Dutch East Indies had nearly stopped. Refineries in Japan were being bombed. Aviation fuel production was collapsing. The quality of remaining fuel was declining. High-octane gasoline required specific refining processes and additives. As supplies dwindled, fuel was cut with lower-grade petroleum or alternative additives that reduced performance and reliability. Pilots reported engine failures and reduced power. Training flights were curtailed to conserve fuel. New pilots entered combat with less preparation than ever before. Aircraft production was similarly affected. Total Japanese aircraft production peaked in 1944 at approximately 28,000 aircraft. In 1945, production declined month by month as raw materials became scarce, factories were bombed, and the transportation system collapsed. By August, when Japan surrendered, monthly production had fallen to perhaps 1,000 aircraft of all types. Even these numbers overstated actual capability, because many aircraft produced were obsolete designs. The Zero remained in production through the war's end, not because it was competitive with the Hellcat, but because transitioning to new designs required resources and time Japan did not have. Better to produce familiar aircraft with existing tooling and supply chains than attempt to introduce new designs that might never reach mass production. Advanced Japanese fighters existed in limited numbers. The Kawanishi N-1KJ Shiden, a land-based fighter derived from a floatplane design, showed excellent performance in testing. It was fast, well-armed, and maneuverable. About 1,000 were built before the war ended. Against the 12,000 Hellcats Grumman produced, 1,000 Shidens could not affect the strategic balance. The Mitsubishi, a 7M Repu, was intended as the Zero's successor, with a powerful engine and better protection. 2 prototypes were completed and showed promise, but the engine, an 18-cylinder radial producing 2,000 horsepower, proved difficult to manufacture in quantity. The complex supercharger required precision machining. The materials needed were increasingly unavailable. The project languished. At war's end, fewer than 10 examples existed. Japanese engineers knew these aircraft were too few, too late. Even if production could somehow accelerate, it would not matter. The industrial base was crumbling. American bombing of Japanese cities was destroying factories, killing skilled workers, disrupting transportation. The home islands were under siege. The captured Hellcat represented everything Japan could not build. Its 2,000 horsepower engine required materials Japan could not obtain, and manufacturing precision the Japanese industry could no longer consistently achieve. Its heavy armor and sophisticated systems added weight that demanded power Japanese engines could not provide. Its 650 caliber machine guns fired ammunition in quantities Japanese production could not sustain. Most significantly, the Hellcat was not a unique prototype or limited production aircraft. It was being manufactured in the thousands. Every American carrier task force had dozens of them. Every strike against Japanese positions included them. They were everywhere, dominating the skies, shooting down Japanese aircraft with casual efficiency. Japanese pilots developed what American intelligence called zero fatigue, though the term applied to all Japanese pilots regardless of aircraft type. It was the psychological recognition that combat with American fighters, particularly Hellcats, was likely to be fatal. Survival requires avoiding engagement whenever possible. Experienced pilots taught new pilots to dive into clouds, to flee toward land, to do anything except combat on American terms. This was the context in which Japanese engineers at Yokosuka examined Charles August's Hellcat. They were not merely studying an enemy aircraft, they were confronting evidence of defeat, tangible proof that the war was lost and had been lost perhaps from the moment it began. Some engineers had warned against war with America. They had understood the industrial imbalance. They had calculated what America could produce given time to mobilize. They had been ignored. Military planners had convinced themselves that Japanese martial spirit would overcome material disadvantages, that American democracy was weak and decadent, that early victories would lead to negotiated peace on favorable terms. All of these assumptions proved catastrophically wrong. American democracy had proven remarkably resilient. Far from being demoralized by early defeats, Americans had been angered and determined. The industrial mobilization had exceeded even optimistic estimates. And peace. Negotiations would occur only after Japan's unconditional surrender. The Hellcat exemplified this. It was not a desperate improvisation or a lucky success. It was the product of systematic engineering, massive industrial capacity, and a nation fully committed to total war. From initial conception to operational deployment took 19 months. From first operational deployment to dominance in Pacific skies took less than a year. From there to war's end, Hellcats shot down 5,156 enemy aircraft while losing only 270 in air-to-air combat. The 19-to-1 kill ratio was unprecedented. It reflected technical superiority, yes, but also tactical doctrine that exploited that superiority, training programs that prepared pilots thoroughly, and logistics that kept aircraft maintained and supplied. The Hellcat was a complete weapons system embedded in a military structure designed to win. Japan had no equivalent system. Individual components might be excellent. Some Japanese pilots were skilled and brave. Some Japanese aircraft had specific advantages in narrow circumstances, but the overall system was breaking down. Pilots lacked training. The aircraft lacked fuel. Factories lacked materials. Everything was becoming scarce simultaneously as American pressure increased from all directions. By early 1945, Japanese strategy had devolved to special attack tactics. Kamikaze, the divine wind, suicide attacks by pilots deliberately crashing explosive-laden aircraft into American ships. This was presented as the ultimate expression of Japanese spirit, willingness to sacrifice everything for the emperor and nation. In reality, it was an admission that Japan could no longer compete in conventional air combat. Kamikaze tactics emerged from desperation. Poorly trained pilots flying obsolete aircraft had minimal chance of surviving combat with Hellcats long enough to reach targets and deliver conventional attacks. But if the pilot intended to die anyway, if the aircraft was essentially a guided missile, then training requirements decreased and effectiveness per sortie increased. The calculus was brutal. A kamikaze attack might have a 10% chance of hitting a ship, but that was better than a conventional attack's 1 or 2% chance given the skill disparity and aircraft mismatch, and the pilot was expended either way. Better to guarantee his death achieved maximum possible damage than to send him into combat where he would die accomplishing nothing. This was the logic of defeat, the reasoning of a military that had lost the ability to fight conventionally and was grasping at desperate measures. And even kamikaze attacks, for all their shock value and the casualties they inflicted, could not change the war's trajectory. American ships had radar, fighter direction officers, combat air patrols, and massed anti-aircraft fire. Most kamikaze aircraft were shot down before reaching targets. Those that got through often hit smaller vessels or inflicted damage the Americans could absorb. Japanese engineers knew this. They could calculate the numbers. They could see the trend lines. Every month brought fewer resources, fewer trained pilots, fewer operational aircraft. Every month brought more American pressure, more air raids, more submarines interdicting supply lines. The end was approaching with mathematical certainty. The captured Hellcat was simply one more data point in an overwhelming pattern, but it was a particularly clear data point, impossible to misinterpret or rationalize away. Here was physical evidence of American capability, not propaganda, not exaggerated claims, but an actual aircraft that could be measured and tested and understood. And understanding it required confronting the reality that Japan could not build an equivalent, could not match the performance, could not produce them in necessary quantities, even if the engineering problems were solved. The Hellcat demonstrated that Japan had lost the industrial war before the first shot was fired in the military war. Some historians have suggested the captured Hellcat's examination in early 1945 had minimal impact because by then Japan's defeat was already certain. This misses the point. The Hellcat's significance was not that it changed Japanese strategy or inspired new developments. Its significance was in forcing Japanese engineers to confront truths they had perhaps suspected but could no longer deny. The war was lost. It had been lost from the beginning, not through any failure of courage or skill or tactical cleverness, but through overwhelming material disadvantage that could not be overcome. The Zero's early successes had been possible only because America had not yet mobilized its industry for war. Once that mobilization occurred, the outcome was inevitable. This was the psychological burden Japanese engineers carried through the final months of the war. They continued, working because duty demanded it. They continued trying to improve Japanese aircraft because their country needed whatever advantages could be gained. But they knew, with the certainty that comes from examining enemy equipment firsthand, that their efforts would not change the outcome. Lieutenant Commander Charles August, whose forced landing had provided the captured Hellcat, survived his captivity and was liberated when Japan surrendered in August 1945. He returned to the United States, resumed his naval career, and lived a long life. In a strange twist of fate, he had been a prisoner of war twice. The first time was in November 1942 when he was shot down, flying an F6F Wildcat during Operation Torch, the landings in North Africa, and captured by Vichy French forces. He was repatriated when Vichy capitulated and returned to duty. His second capture, in January 1945, resulted in 9 months of brutal treatment in a Japanese prisoner of war camp near Tokyo. He survived through a combination of luck, resilience, and the surrender that came in August before he could be executed or worked to death. August credited his survival to the support of fellow prisoners and the knowledge that American forces were winning and would eventually liberate them. The Hellcat he left behind, Bureau number 71441, was destroyed at some point, either deliberately by retreating Japanese forces or as collateral damage during bombing raids. When American occupation forces arrived at Yokosuka Naval Air Station after the surrender, they found the facility extensively damaged. Some captured American aircraft remained, including possibly sections of the Hellcat, but the complete aircraft did not survive. Photographs taken during the occupation show various captured American aircraft in Japanese markings, documentation of the intelligence efforts both sides conducted throughout the war. These images are preserved in archives, reminders of the lengths militaries go to understand enemy capabilities. The broader story of the Hellcat's combat record needs little elaboration. 5,156 enemy aircraft destroyed, 305 Hellcat aces created, 19-to-1 kill ratio maintained across 2 years of combat. These statistics speak to the aircraft's effectiveness and the system that employed it. Commander David McCampbell, the Navy's top ace with 34 victories, flew Hellcats exclusively. He described the aircraft as outstanding, easy to fly, stable, rugged, and easy to maintain. Ensign Robert Duncan of Fighting Squadron 5 became the first Hellcat ace, achieving 5 victories and eventually 7 total. Hundreds of other pilots achieved ace status flying Hellcats, more than any other American aircraft. The Hellcat's versatility extended beyond air-to-air combat. Fighter-bomber variants carried 2,000 pounds of bombs and rockets, providing devastating ground support for amphibious operations. Night fighter variants with radar pods intercepted Japanese night bombers that had previously attacked with impunity. Photographic reconnaissance variants conducted crucial intelligence missions. 12,275 Hellcats were produced by Grumman at Bethpage, Long Island, between October 1942 and November 1945. Production in 37 months equaled Japan's total zero production over 9 years from 1936 to 1945. This comparison alone illustrates the industrial disparity. The production rate peaked in March 1944 at 644 aircraft. At that rate, Grumman was producing more Hellcats in 6 weeks than Japan produced Zeros in 6 months. And Grumman was just one factory. American industry was simultaneously producing Corsairs, Thunderbolts, Mustangs, Lightnings, and dozens of other aircraft types. The scale remains difficult to comprehend even decades later. Modern historians examining production records marvel at what was achieved. The United States built 96,000 aircraft in 1944 alone. For comparison, Germany produced approximately 40,000 aircraft that year, and Japan approximately 28,000. America was outproducing both Axis powers combined by more than 2 to 1. This production required millions of workers, thousands of factories, vast quantities of raw materials, sophisticated logistics networks, and economic organization on a scale never before attempted. The fact that it succeeded speaks to American industrial capacity and organizational ability, but numbers alone do not capture the human cost. Every aircraft produced represented thousands of man-hours of labor. Every aircraft shot down represented a pilot killed or captured. Every victory in the statistics was someone's death. Japanese pilots dying in burning Zeros or shattered bombers, families receiving telegrams, communities mourning losses. The Hellcat's 19-to-1 kill ratio meant 19 Japanese pilots died for every American Hellcat pilot killed in air-to-air combat. Over 2 years, that meant thousands of Japanese pilots killed in unequal contests against superior equipment flown by better-trained adversaries. Many of those Japanese pilots were teenagers or very young men with minimal training, thrown into combat because Japan had no choice. War reduces complex realities to statistics, but behind every statistic are individuals. Charles August was one person whose aircraft happened to be captured. The Japanese engineers at Yokosuka were individuals trying to do their duty despite understanding their efforts were futile. The pilots who died in combat on both sides were individuals with families and futures that ended violently. The captured Hellcat's significance lies not in changing history, but in revealing it. The aircraft provided Japanese engineers tangible evidence of what they already suspected, that they were fighting a war that could not be won against an opponent whose resources were overwhelming. This knowledge changed nothing strategically, but everything psychologically. Continuing to fight when victory is impossible requires either ignorance or determination bordering on fanaticism. Japanese military culture emphasized duty, sacrifice, and service to the emperor regardless of circumstances. Soldiers and sailors and airmen fought to the end on island after island, dying in battles that accomplished nothing except delaying the inevitable. Engineers at Yokosuka had no such illusions. They understood the reality. They had examined the Hellcat. They had measured its components. They had calculated what it would take to match it. They knew Japan could not do so, and they understood what that meant for the war's outcome and for their nation's future. This knowledge was a burden distinct from combat itself. Warriors can face death with courage when they believe in their cause and trust their leaders. But continuing to work when you know your work will not matter, when you understand that all the effort and sacrifice will end in defeat, requires a different kind of determination. Some Japanese engineers hoped that by prolonging resistance, they might achieve a negotiated settlement that preserved something of the nation and prevented complete occupation. Others worked simply from duty, believing that doing their best was an obligation regardless of outcome. A few may have hoped for miracles, for some unforeseen development that would change everything. But examining the captured Hellcat made clear there would be no miracles. American industry was producing weapons Japan could not match. American pilots were trained to standards Japan could not achieve. The American strategy was methodically crushing Japanese resistance through overwhelming material advantage. The end would come through either surrender or complete destruction. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. In August 1945, Emperor Hirohito made the decision his military leaders could not. He announced Japan's surrender following the atomic bombings of Hiroshima and Nagasaki. The war was over. Japanese engineers at facilities like Yokosuka ceased their work. American occupation forces arrived to document Japanese technology and ensure demilitarization. The industrial war had been decided years earlier. The military campaigns were simply working out the inevitable conclusion. The Hellcat represented that inevitability in physical form, an aircraft that Japanese engineers could examine but not replicate, understand but not defeat. Modern historians studying World War II often focus on battles and campaigns, the dramatic events that make compelling narratives. But wars between industrial nations are won or lost in factories as much as battlefields. The nation that can produce more weapons, train more soldiers, and sustain longer campaigns will prevail if its political will holds. America's political will held. Despite early defeats and heavy casualties, American resolve did not break. Industrial mobilization continued. Production increased. More ships, more aircraft, more tanks, more of everything needed to prosecute war on a global scale, against multiple enemies simultaneously. Japan's calculation that America lacked the will for extended war proved catastrophically wrong. Every assumption underlying the Japanese strategy was wrong. The war would not be short. Early victories would not lead to negotiated peace. American resolve would not collapse. And the Japanese fighting spirit, however genuine, could not overcome material disadvantages measured in orders of magnitude. The captured Hellcat demonstrated this reality more clearly than any propaganda or intelligence assessment could. It was physical evidence that the gap between Japanese capability and American capability was unbridgeable given time and resources available. Japanese engineers who examined it understood, and that understanding, perhaps more than any single military defeat, made clear that continuing the war was futile. The tragedy is that this understanding came too late, or perhaps came earlier but was ignored by political and military leaders unwilling to accept unpleasant truths. The war continued for 7 months after the Hellcat was captured. 7 months of continued killing on both sides. 7 months of cities burned and ships sunk and aircraft shot down. 7 months that changed nothing about the eventual outcome but cost thousands more lives. Could those lives have been saved if Japanese leadership had accepted reality sooner? Historical counterfactuals are impossible to prove, but the question haunts. Engineers at Yokosuka knew by January 1945 that the war was lost. Others knew even earlier. Yet the fighting continued into August, until atomic weapons provided justification for accepting what should have been accepted long before. The story of the captured Hellcat is ultimately a story about the cost of ignoring reality. Japan started a war it could not win against an opponent whose resources were overwhelming. Early tactical successes obscured strategic impossibility. By the time reality became undeniable, hundreds of thousands were dead and Japan faced complete defeat. The Hellcat that Charles August left on Formosa in January 1945 was simply one piece of evidence among many. But it was particularly clear evidence, impossible to rationalize or misinterpret. Here was what America could build. Here was what Japan faced. Here was proof that the war was lost, and had been lost from the beginning. Japanese engineers who examined that aircraft carried the burden of knowing this truth while their nation continued fighting. They continued their work because duty demanded it, but they understood their efforts would not change the outcome. That psychological burden, continuing to work when you know your work is futile, may be the captured Hellcat's most profound legacy. The aircraft itself was destroyed and forgotten, but what it revealed, the technological and industrial chasm between America and Japan, shaped the war's final months and informed post-war understanding of why the Pacific War ended as it did. Material advantages matter. Industrial capacity matters. And sometimes, examining a single enemy aircraft can reveal truths that thousands of words cannot convey. The 2,000-horsepower engine in Charles August's Hellcat represented more than just mechanical power. It represented American industrial might mobilized for total war. Japanese engineers at Yokosuka understood this when they examined the engine, measured its components, calculated what would be required to replicate it, and realized Japan could not do so. That was the moment of clarity, the collision between belief and reality, between what they had hoped was possible and what evidence made undeniable. The war was lost. It had been lost from the beginning, and all that remained was enduring until the end came, whether through surrender or annihilation. In the end, surrender came first, sparing Japan complete destruction, but leaving a nation shattered by 6 years of war and facing an uncertain future. The engineers who had examined the captured Hellcat survived to work in Japan's reconstruction. Some contributed to Japan's post-war aviation industry, which would eventually become world-class again. Others left aviation entirely, seeking peace in civilian pursuits after years of futile military work. Charles August's Hellcat, Bureau number 71441, exists now only in photographs and archival documents. But its story endures as an illustration of how industrial warfare operates, how technological advantages shape outcomes, and how sometimes a single captured weapon can reveal truths that change understanding even when they cannot change history. The gap between Japanese and American capability in January 1945 was unbridgeable. The captured Hellcat proved it, and that proof, delivered through engineering analysis rather than propaganda, made the truth impossible to deny for those who examined the evidence with clear eyes.